All right, today we are looking at rate of change. Now, what is rate of change? Rate of change compares a change in one quantity to a change in another quantity. Pretty much rate of change is just a fancy way of saying slope. And one reason why we'll use rate of change instead of slope in the rest of this unit is because rate of change addresses that the slope on certain functions will be constantly changing, especially in exponential functions. So in exponential functions, our slope, the rate of change between our points, is constantly changing. Now, a linear equation, that rate of change, that slope is going to be constant, but with our exponential functions, we'll be referring to it as rate of change. Now, to find a rate of change, it's the same equation as finding a slope. It's still rise over run, your change in y over change of x. You could also look at that as delta y over delta x. That triangle means delta, which means change in Greek. Given 2 points, x sub 1 and y sub 1, and x sub 2 and y sub 2, the formula is also the same as slope. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So that's remaining the same. Let's look at a few problems in which we're going to find the slope that passes between the 2 points. So we have the ordered pairs -7, 1 and 1, 5. Now once again, we're finding the slope, which we talked about. A fancy way of saying that is rate of change, which we shorthand as ROC. So to find the rate of change, we have x1, y sub 1, x sub 2, y sub 2. So we get 5 minus 1 over 1 minus -7, which will equal 4 over, this will become 1 plus 7, so 8. So our slope, our rate of change between those two ordered pairs is 1/2. Now too, we're looking at the ordered pairs 3, 0 and 8, 0. So we can go ahead and label x sub 1, y sub 1, x sub 2, and y sub 2. So our rate of change, keep in mind a fancy way of saying slope, is 0 minus 0 over 8 minus 3. So this expression equals 0 over 5. 5 goes into 0, 0 times. So here our rate of change is 0, and that would be a horizontal line. We have a slope that's undefined for vertical lines. All right, next we're going to take a look at some graphs. So we're told Janet took a 5-hour walk. The graph shows her cumulative mileage at each hour. So meaning at 0 hours she walked 0 miles, at 1 hour she walked 3 miles, at 5 hours she walked 14 miles total. So we're asked to consider the time interval between each hour. Determine the time interval that Janet walked the most miles. So that one we're looking for her rate of change. So we can take a look at this graphically and see where the line increases at the steepest rate. And it appears to increase the steepest between 1 hour and 2 hours. So between the first and second hour. Now, we can also prove that algebraically by finding the slope. Now keep in mind we can find the slope algebraically, but we can also look at it graphically. So keep in mind it's going to be the rise over run. So between 0 and 1 hour, we have a rise of 3 over 1, so she went 3 miles. From 1 to 2, she went from 3 miles to 8 miles, so she went 5 miles. So 5 over 1 would just be 5. From hour 2 to hour 3, she had no rise, so she actually went 0 miles. From hour 3 to hour 4, she went from 8 to 10, so she went 2 miles. And from hour 4 to hour 5, she went from 10 to 14, so she went 4 miles. So that's also how we could prove it algebraically, by finding that rate of change. And keep in mind the reason why we can just say 5 miles is because all of these are going to be over 1 hour, since we're looking from 1 to 2, 2 to 1, 3 to 4, 4 to 5, so we don't necessarily have to put that 1 underneath. So she walked the most miles. She walked 5 miles between the first and second hour. Now, B, we're asked to determine the time interval that Janet covered the least miles. So that least miles labeling also helps there. She covered between the second and third hour because she went 0 miles. Her mileage did not change. So we could assume maybe for the second and third hour she took a break, she stopped, she maybe got something to eat, ran into a friend, or was talking to them. So her mileage did not change. So she was stagnant. She didn't go anywhere. All right, now let's take a look at this on exponential function. So the following. All right, now we're taking a look at the data that shows the number of species that have gone extinct since 1800. So this is actually real data. So from the graph, we're asked to estimate the rate of change from 1920 to 1950. Now that rate of change, we know the change in our x values, that's going to be 30, because there are 30 years separating that. So to find the number of extinctions, we're going to be seeing how many units we rise up from 1920 to 1950. So 1920, this mark here is 5,000. So 1920 appears to be about 1,000, and 1950 appears to be about 5,000. So we went from 1,000 to 5,000 extinctions, so that's a change in 4,000. All right, so we always want to simplify. So our rate of change we can estimate to be 400 extinctions per 3 years. So it increased 400 extinctions of species every 3 years. Now B, we're asked to algebraically find the rate of change from 1980 to 2010. So we're going to be using the formula. So my ordered pair for 1980, I know that's my x value. If I go up to 1980, so in between here is 15,000. It's not quite at 15,000. So I'm going to say it's approximately 14,000. And then my next ordered pair in 2010, there was approximately, so between here is 35,000. I would say that's approximately 37,000 extinctions. All right, so the rate of change between those, and we can label just as we did on the third slide, x sub 1, y sub 1, x sub 2, y sub 2. So we have 37,000 minus 14,000 over 2010 minus 1980. So the bottom will be 30, so we're back at 30 years. And then the top, we are at 23,000. So 23,000 extinctions. And once again, we divide out the 0 there. So algebraically, the rate of change from 1980 to 2010 was 2,300 extinctions per 3 years. Now, since our rate of changes between these 2 years are with the same denominator, so it tells us every 3 years, we can see that the number of extinctions from 1980 to 2010 increased at a more faster rate than they did from 1920 to 1950 due to that smaller number. Now we could also take a look at the algebraically. From 1920 to 1950, we're not seeing a whole lot of vertical growth. But from 1980 to 2010, we're seeing a whole lot of vertical growth comparatively. So we can use this to compare as well. All right, hope you have a great evening. Please make sure to bring your textbooks to class tomorrow. I will see you later.